Hello and welcome to Chapter 4, Number Theory and Cryptography. This is CCCS122, Discrete Mathematics at the University of Jeddah. So this chapter is about number theory, which deals with integer operations, integers and their properties. We'll start with a couple of basic principles such as divisibility, greatest common divisors, least common multiples, modular arithmetic, and we'll look at a number of algorithms as we go along. So if we have two integers a and b, in which the only condition is that a is not 0, we say that a divides b if there's an integer c, so that b is equal to a times c. When a divides b, we also say that a is a factor of b, or that b is a multiple of a. We have new notation for that, and this is what that notation looks like. A divides b. That's how we read that. We also have something for cases where a does not divide b, and this kind of looks like multiplication, but you have to be aware of the context in which it is being used to make sure you're not confusing this symbol with the multiplication symbol. Now, if we have three integers a, b, and c, then if a divides b and a also divides c, then we can say that a divides b plus c. And as an example over here, we have 3 divides 6, which it does, of course, and 3 divides 9, which it also does. And 6 and 9 add up to 15, which also means that 3 also divides 15, which we also know it does. If a divides b, then a also divides bc, as long as c is, of course, also an integer. And as an example, so if we know that 5 divides 10, and it also means that 5 divides 20, divides 30, divides 40, any integer multiple, all integer multiples of 10. And if a divides b and b divides c, so this is kind of like a chain rule over here, then a also divides c. Example for that here is 4 divides 8, of course. 8 divides 24. That means that 4 also divides 24. Now, a positive integer p greater than 1 is called a prime if the only positive factors of p are 1 and p itself. So basically, if a positive integer can only be divided by 1 or itself. A positive integer that is greater than 1 but is not a prime is called a composite number. Every positive integers can be written uniquely as the product of primes, something you've hopefully been doing since grade school. And usually the way we write it out is we put the prime factors in ascending or in order of increasing size. So as an example, 15. 15 can be written as the product of prime numbers 3 and 5, and according to this in this notation, we usually put the smaller factors in front. So 3 comes before 5. So 48, just like that, can be written as the product of 2 times 2 times 2 times 2 times 3, or written more neatly as 2 to the power 4 times 3. 17 is a prime number, of course. So 17 cannot be broken down any further. 100 is 4 times 25, and 4 can be written as 2 times 2. 25 is, of course, 5 times 5, so we can write that as 2 times 2, 2 square, times 5 square. 512 is the 9th power of 2, something that you should always know as a computer science student, the powers of 2. 515 is 5 times 103, and 103 is a prime number. 28 can be factorized as 2 times 2 times 7, or 2 square times 7. Now, if n is a composite integer, then n has a prime divisor less than or equal to under root n. And this is kind of easy to see. If n is a composite integer, it must have 2 divisors at least, say p1 and p2, so that when you multiply p1 and p2, you get n. You could have more, of course, but 2 at the very least, if it's a composite integer. And p1 will be greater than or equal to 2. p2 will also be greater than or equal to 2. Remember, we don't include 1 as a factor when we factorize composite numbers. So p1 and p2 cannot both be greater than under root n. So because that would make p1, p2 larger than n. Okay. The smaller number, the smaller of p1 and p2 is not a prime number itself, then that can be broken up into further prime factors, and those of course will be even smaller than itself, but still larger than 2. So let a be an integer and d a positive integer. Then there are unique integers, q and r, in which r is 0 or less than d. So between 0, including 0, up to less than d, such that a is d times q plus r. Here a is called the divisor. So d is called the divisor. A is the dividend, q the quotient, and r the remainder. Now when we divide, as an example, if we divide 17 by 5, that means 17 in place of a, we have 5 in place of d, and we have 3 in place of q, and we have 2 in place of r. You can also think of this as, or perhaps easier to remember, is that 17 is the number being divided by 5, which is equal to 3. Remember, we're dealing in integers only, and the remainder of dividing 17 by 5 is 2, the remainder. So that's what we have over here, R for remainder. So 17 here is the dividend, 5 the divisor, 3 the quotient, the result from the division, and 2 is the remainder. Another example, this one of a negative integer. So what happens if we divide minus 11 by 3? This one might seem a little strange at first, but check this. The remainder has to be specified, that must be positive. Now when you're dividing a negative number, it means that in this case 3 times minus 4 is minus 12, and that is of course too small, so you have to add something to that, and the thing that you add is the remainder. Add 1 to minus 12 and you get minus 11. The remainder cannot be negative. That's the key thing to remember over here when dealing with performing integer division of negative integers. So minus 11 here is the dividend, 3 the divisor, minus 4 the quotient, and 1 the remainder. Okay, now let's talk about the greatest common divisor. Let's go through this a little more quickly. So let A and B be integers again, not both of them, both not 0. So the largest integer D that divides A and also divides B is called the greatest common divisor, or also commonly abbreviated as GCD. And that's also written in function form, like this. So the GCD of A and B. Here's an example. What is the GCD of 48 and 72, for example? So positive common divisors of 48 and 72 are many. 1, 2, 3, 4, 6, 8, 12, 16, 24 are all divisors that divide both 48 and 72. But the GCD is the greatest among them. So that would be, in this case, 24. Another example, what is the GCD of 19 and 72? Now, quickly see that 19 is a prime number, which means it is only divisible by 1 and 19. Now, if 72 is not divisible by 19, then the only integer that remains that could be their common divisor is 1. And so the GCD of 19 and 72 is 1. Now, one way to find the GCD is using prime factorizations. So consider you have two integers A and B, and you want to find the GCD. Now, what we can do is we can factorize both these numbers. So you could have different prime factors, prime factor 1, prime factor 2. So basically, and they can, of course, appear multiple times as factors of A. That's what those exponents represent, just like we saw a few slides earlier. And we can do the same thing for the other number B. Same prime factors, of course, P1, P2, all the way up to some Pn. And each of them appears b1, b2, all the way up to bn times. So then the GCD of A and B can be found like so. Basically, the prime factor P1 to the power of whichever is the smaller of A1 and B1. The second prime factor P2 and to the power of whichever one is the smaller between A2 and B2. And so on, all the way up to the last prime factor. I know this looks like a lot of math, so it's better seen as and understood by example. And then you can come back to this notation, and I'm sure it'll make sense. So as an example, we have, for number A, we have 60. 60 written as prime, in terms of its prime factors, is 2 to the power 3 times 3 to the power 1 times 5 to the power 1. And then we have the other number B, let's say 54, which can also be written as, in terms of its prime factors, 2 to the power 1, 3 to the power 3, and 5 to the power 0. So basically 5 is not really a factor of B, but 54, but we just put it here because 5 appears as a prime factor in the other number, A. Okay. So then the GCD, according to this equation that we have up here, would be 2 times 3 times 5, and the powers will be whichever is the smaller out of the two between prime factorizations of A and B. So we have for 2, for example, we have 3 and 1. The smaller one is 1, so that's what we put over here in the exponent. For 3, we have 1 and 3, the smaller one is 1, so we put 1 up here. And for 5, we have 1 and 0, and the smaller one is 0, of course, we put a 0 over here. So 2 times 3 times 1 is just equal to 6. And that's what we have. 6 is the GCD of A and B. Now, there's also something called relatively prime integers. What is that? Two integers A and B are called relatively prime if their GCD is 1. That does not mean that A and B are necessarily both prime numbers. That's not a condition. Here's some examples. So 15 and 28. Neither of them is a prime number. 15 can be written as 3 times 5. 28, we already saw, can be written as 2 to the power 2 times 7. But their GCD happens to be 1, which makes them relatively prime integers. We have 55 and 28. Same thing. Their GCD is also 1, which makes them relatively prime. And what about 35 and 28? 35 can be written as 5 times 7. 28 can be written as 2 squared times 7, which means the GCD is 7, which means 35 and 28 are not relatively prime. So if you have more than 2 integers, you have a set of, say, n integers, you can still talk about numbers in that set being pairwise relatively prime if the GCD of every two selected pairs of numbers in this set, if the GCD of all of them, doesn't matter which RAI or AJ, which two numbers you pick, if the GCD of all pairs is 1, then we say that that's a set of pairwise relatively prime numbers. And we don't have to make the set too big to check it out. So let's say we have these set of three numbers, 15, 17, and 27. Are these pairwise? Is this a pairwise relatively prime set of numbers? And if I can find any pair out of these three that have a GCD that's larger than 1, the answer is no. And turns out that the GCD of 15 and 27 is 3. So this set of numbers is not relatively prime. What about 15, 17, and 28? Well, turns out that 3 possible pairs of numbers that you can make correct. 1, 2, 3, right? So as it turns out, this set of 3 numbers is pairwise relatively prime because the GCD of 15 and 17 is 1, the GCD of 15 and 28 is 1, and the GCD of 17 and 28 is also 1. So yeah, all possible pairs have GCD of 1. And related to the greatest common denominator, or GCD, is the least common multiple. So the least common multiple of positive integers a and b is the smallest positive integer that is divisible by both a and b. The notation goes a little similar to the GCD. We usually express it in function form. So LCM function taking 2 arguments a and b. And an example of that is, so the LCM of 3 and 7 is 21. 21 is the smallest integer that is a multiple of both 3. Is the smallest, not a multiple, is the smallest integer that is divisible by both 3 and 7. The LCM of 4 and 6 is 12. The LCM of 5 and 10 is 10. And we can find the LCM using, again, a method using prime factorization. This is similar but slightly different in one step, so pay attention. So we have 2 integers a and b, and we factorize them into prime factors, just like we did for the GCD case. And then the LCM of a and b is defined like this. The difference over here is that instead of the min function, like we had for the GCD, we use the max function up here. So basically we use the larger of the 2 exponents, a1 and b1, the larger of the 2 exponents between a2 and b2. And again, let me show you this by way of an example. So we have a equal to 60, which can be factorized into these prime factors: 2 to the power 2 times 3 to the power 1 times 5 to the power 1. And the other number b is 54, which can be factorized into 2 to the power 1, 3 to the power 3, and 5 to the power 0. Now, if you want to find the LCM of these 2 numbers, 2, out of 2 and 1, the larger exponent is 2. For 3, we have 2 exponents, 1 and 3. The larger one is 3. And for 5, we've got exponents 1 and 0, and the larger one is 1. Pick that. So we got 4 times 27 times 5, and if you work that out, it comes out to 540. And that is the LCM of 60 and 54. So once again, prime factorization for GCD. Pick the terms with the lowest powers for each base. So for 2, 3, and 5, pick the ones with the lower power. So for 2, that would be 2 to the power 1, 3 to the power 1, and for 5, 5 to the power 0. Multiply them and you get 6 in this case. And that is how you find the GCD of 2 integers. And for the LCM, you kind of do the opposite. You pick out of the 2 terms to pick from, you pick the one with the higher exponent. So 2 to the power 2, 3 to the power 3, 5 to the power 1, and you multiply those together and you get 540, of course. And then there's a theorem, of course, that you can also multiply. So the product of A and B equals the product of their GCD and their LCM. Because it's all the same terms, just arranged differently in different order. Okay. Now, let A be, let's move on to modular arithmetic. So let's take A, an integer, and M be a positive integer. Then we can, we denote by A mod M, the remainder of when A is divided by M. So simple example, 9 mod 4. What happens when you divide 9 by 4? You get 2, but what is the remainder? You will have a remainder because 4 does not divide 9. So there's a remainder, and that remainder happens to be 1. On the other hand, if you divide 9 by 3, 3 does divide 9, which means there will be no remainder in integer division. The remainder is 0. 9 mod 10, well, 10 does not divide 9, and we get the whole 9 as a remainder of that integer division. And we use that same notation for negative integers, of course. So minus 13 mod 4, and the remainder of that is 3. Okay. So let's have A and B be integers and M be a positive integer. We say that A is congruent to B. So we're talking about new concept here, congruences. We say A is congruent to B modulo M if M divides A minus B. Okay. I'll show you some example for that. That'll clear that up somewhat. So we have new notation for that. So this is how you would write it in English, of course, but the way to write that is like this. And you read that as A is congruent to B modulo M. So in other words, A is congruent to B mod M if and only if A mod M is equal to B mod M, which means that A and B have the same remainders when divided by M. here's an example of that, some examples actually. So, question: is it true that 46 is congruent to 68 modulo 11? And the answer is, well, question is, does 11 divide A minus B? And the answer is yes, 11 actually does. So 46 minus 68 is how much? Minus 22. Okay, and 11 does divide minus 22. Another one. Is it true that 46 is congruent to 68 modulo 22? And the answer is yes. So it's the same numbers. So again, 46 minus 68 is minus 22. And yes, 22 does divide minus 22. So 46 is congruent to 68 modulo 22. And you can also ask a question: for which integers z? Is it true that z is congruent to 12 modulo 10? And there can be infinitely many answers to that. So basically, what numbers of z can I have that z minus 12 gives me numbers that are divisible by 10? So that would be infinitely many numbers. Starting off here, so 2, of course, because 2 minus 12, start with 12. So 12 minus 12 is 0, 0 is divisible by 10. 22 minus 12 is 10, 10 divided by 10, that also works. And so basically, all numbers above and beyond at differences of 10 is the answer over here. And then there's the theorem to add. Let m be a positive integer. Integers a and b are congruent modulo m if and only if there's an integer k such that a is equal to b plus km. Okay, here's another 2. Let m be a positive integer again, and let's say a is congruent to b modulo m and c is congruent to d modulo m. Then, can we prove these two theorems? A plus c is congruent to b plus d modulo m, and ac is congruent to bd modulo m. Now, this is actually not that hard to prove. So now that we have the previous theorem that can convert this congruence into an equality. Okay. So let me show you that. So what this means is basically b is equal to a plus s times m. S is some integer, a positive integer, a multiple. And just like that, for the other congruence, d is equal to c plus tm. T again being some integer. Now that we have converted these two congruences that we have into two equations, we now have more tools, more options on our hands. What we can do is we can add these two equations, call them 1 and 2. We can add them together, and that gives us b plus d on one side and A plus SM plus C plus TM on the other. Then we can move things around and change it to this, which is basically to say that B plus D is equal to A plus C plus some integer multiple of M. What we had appear as, so this is this S plus T term. S plus T term is basically equal to that K integer that you saw previously. And so that proves this congruence up here. And to prove the other, in which A and C and B and D multiplied together, you can take these same two equations, 1 and 2, you can just multiply them together. So we get BD on one side, and we get A plus SM times C plus TM on the other. You open that up, and you end up with AC, this term over here, and you end up with, take out M as a common factor, and you end up with all these other terms over here. But the important thing is that A, T, C, S, S, T, M, these are all integers, which means that all of this is an integer term. Okay. Now there's an algorithm that we can use to find the greatest common divisor of two integers A and B. So we had the prime factor method, of course, and here's yet another one. So if we want to find the GCD of 287 and 91, we divide 287 by 91. So divide the larger by the smaller. Okay. So you do that, and you end up with a quotient and a remainder. Okay. All right. So the remainder is non-zero, which means 91 does not divide 287. And so what ends up happening is, we know that for three integers A, B, and C, if A divides B and then A divides, then that means that A divides BC for all integers. Okay, so therefore any divisor of 91 will also be a divisor of 91 times 3. We know that. We also know that for three integers, if A divides B and A divides C, then A also divides B plus C. And therefore, any divisor of 287 and 91 must also be a divisor of 287 plus 91 times any integer multiple. 14. So, for that reason, the GCD of 287 and 91 must be the same as the GCD of 14, that remainder that we had, and 91. So the GCD of these two numbers that we're trying to find is also the GCD of 14 and 91. But now I have to deal with smaller numbers. So in the next step, I basically repeat the same iteration that we just performed. I divide 91, this time by the remainder, 14. You do that, you divide 91 by 14, and the quotient is 6. There is a remainder from that, and that remainder is 7. And again, that means that the GCD of 14 and 91 is the same as the GCD of 14 and the remainder, 7. The non-zero remainder, 7. As you can see, and so we go into the next iteration. So we divide 14 by 7, and you can see that 7 does divide 14. The quotient is 2. The remainder is 0. And that makes 7. That makes 7, the GCD of the original two numbers, 287 and 91. This is the pseudocode for this Euclidean algorithm. And let's move on to representations of integers. So let b be a positive integer greater than 1. And then if n is a positive integer, it can be expressed uniquely in the form something to the power b to the power k, a multiple of b to the power k minus 1, all the way down to some multiple of b plus some remainder a0. Over here, k are non-negative integers. I know this again seems like a lot of theoretical stuff, but hold on, we'll get to much more familiar territory over here in a second. These terms a0, a1, all the way up to ak are non-negative integers less than b. And the highest one of them, ak, is not equal to 0. The other ones, ak minus 1, ak minus 2, a2, a1, a0, any of them are allowed to be 0, just not the highest order term. And here's what that can look like. If we have the number 859, we can also think of that as 8 times 100 plus 5 times 10 plus 9 times 1. And what are the 100, 10, and 1 over here? Well, 100 is just 10 to the power 2, 10 is just 10 to the power 1, and 1 is just 10 to the power 0. This is basically b squared, b to the power 1, b to the power 0. b is the base of our numbering system, 10. Now you know that. By now you know that numbering systems can have different bases. So, for example, we've seen the binary number system a couple of times now. So, in a numbering system where the base is 2, binary number system, for example, we could expand this 5-digit binary number like this and easily convert it to decimal, of course. So, 1, it's this one. This is the 0, 1, 2, 3, 4. I'm just going to number these digits. So 2 to the power 4, that's what I have over here, multiplied by 1, the digit I have over here. Then I have 0. I'm just going to skip the 0 digits because they're not contributing anything. Then I have another 1 over here. That's this one. It's multiplied by 2 to the power 2. Then I have another one coming right after that. And the weight of that is 2 to the power 1. So I've got 2 to the power 4, which is 16, plus 4 plus 2, which all add up to 22 in our familiar decimal system. Just to show you what's possible. And also, I mentioned that also in an earlier chapter that there's also something called the hexadecimal numbering system, which has a base b of 16. And typically we use letters A, B, C, D, E, and F for the additional digits that in the decimal numbering system would be the numbers 10, 11, 12, 13, 14, and 15. So we have over here this hexadecimal number 3A0F in base 16 in the hexadecimal numbering system. Let's convert that to decimal. Done easily enough using the same procedure we used up here for the binary number. So we got 3, and the weight of this 3, the value of this 3, this digit is, so this is to the power 0, to the power 1, to the power 2, to the power 3, so 16 to the power 3. We have A. A is equal to 10 in the decimal system, and the weight of the position it's in makes the weight of this digit 16 squared, 16 to the power 2. Then we have a 0, so we don't have to do anything for that. And then we have F over here. F is equal to the number decimal number 15. It's in position 0, so 16 to the power 0. It's basically just 1. So you can use your calculator, work this out, and it comes out to 14,863 in the decimal numbering system. And this is how you can convert from any base to decimal. Now, what about the reverse? Let's say you have an integer n. How do you write that integer n in base b format, whatever the value of b is, 2, 8, 16? The first thing to do is you divide n by b. You get a quotient and a remainder. The remainder, as you can see, I'm calling it A0, becomes the lowest, the rightmost digit in the base B representation of number n. And then you take the quotient and you divide it by B again. And that will give you the next digit in the base B expansion of this integer, until the quotient becomes equal to 0. So the next digit you get is A1 and Q1. Q1 is then again divided by B, and you get from that Q2 and remainder A2. A2 becomes the third digit, and so on. So let's say you have this decimal number over here, 12,345, and you want to write its base 8, its octal number representation. You can do that by following this algorithm, and let's do that as an example. So first we divide 12,345 by 8. You do that, and you get 1,543, and you get a remainder of 1. And you take the 1,543 and divide it by 8 again, and you get 192 and remainder 7. Then you take the 192 and you divide them again by 8, and you get as a result 24 and a remainder of 0. You divide 24 again by the base 8, and you get as a result 3 with remainder 0. And then you take 3 and divide it by 8 again, and you get as your quotient 0 and remainder 3. Your quotient is now 0, which means we end it over here. And question now is, what is the octal representation of 12,345 in decimal? Yeah? The answer is all of these remainders. If you put them in order, so the last one is the highest digit, the first one is the lowest digit. 30071. 30071. That's the base 8 representation of 12,345 in base 10. That's how you can convert one to the other. And you can do that from base 10 into any other base. Base 2, base 16, whatever you need. This is the pseudocode representation of this algorithm that you just used. This might be in one of your future homeworks or assignments, maybe. Okay. At this point, also remind ourselves of how we human beings learn to add two integers, and based on that, we can generalize that to understand how to add numbers of other numbering systems. So the way it usually works is this. Have two numbers, align the digits, put them one on top of the other, and you add a little on the side. You start and with the lowest significant, the smallest digits. 3 plus 2 equals 5. 8 plus 3 equals 11. So you put the 1 down there, and the overflow, the next becomes a carry digit. You put that on top of the next digit, the one in third place over here. Now you add 1 and 5 and 9, and you get from that 15. So you put a 5 down here, and you put another carry digit on top of the fourth digit. Now you add 1, 7, and 4, and from that you get 12. Leave the 2 down here, and you have yet another carry digit, but you've got basically zeros over here, and we just add 1 plus 0 equal to 1, and the answer is, of course, 12,515. That's how you've been adding numbers since grade school, of course. How does that work for binary numbers? Pretty similarly, actually, if you think about it. You put the numbers one on top of the other, align the digits, and then you start adding. So 1 plus 0 in binary makes 1. For the next digit, we have 1 plus 1. Now, there's no 2 in binary numbers. There's only 1, 0. So 1 plus 1 in binary equals 1, 0. So you put the 0 digit down here, and the other digit becomes a carry. And then you add 1 plus 0, and the answer is 1. And then for the digits in fourth place, you add 1 plus 1. We already had that situation. The result will be 1, 0. Leave the 0 down here, add another carry bit, and that is now added to 0 and 0. So we get 1, 0, 1, 0, 1 as the sum. And it works the same way for base 8. It works the same way for base 16. The only thing that changes is that for base 8, as soon as the result becomes larger than 7, you get a 2-digit number and you have to do a carry operation. In base 16, as soon as the result of adding 2 or 3 digits becomes larger than 15, you have a 2-digit number in that intermediate result, and you have to perform a carry operation again. Okay. What we just did, kind of like the way we do it on paper, you can describe the same thing, you can describe the same operations algorithmically. And that description is a little more wordy at first. So what you do is, again, we basically started with the rightmost digits in positions 0 and 0, A0 and B0, A0 and B0, added them together, and the result was a sum, and maybe we have a carry. So this is all being written here, assuming we're doing binary number addition, okay? So S0 is the rightmost digit of the sum, the result that you're getting. And then for the next digit, you have the carry from the previous operation, plus you add A1 and B1, and the result will give you again 2 digits, so S1, and maybe a carry digit, which can be again 0 or 1 in the binary case, and so on, until you obtain carry digit Cn minus 1, which might become an additional digit in the sum, Sn. Okay. So here are two numbers, an example of two numbers using that are two binary numbers being added using this algorithmic method. A little slow, looks a little long, but here it is anyway. So we start by adding A0 and B0, which are 0 and 1, 0 and 1, and the result of that is 1. Carry digit is 0, so carry digit is 0, sum digit is 1. And then we move on to adding A1, B1, and the carry digit from the previous operation, C0. And those are 1 and 1 and 0. 1, 1, and 0. And that gives us a sum digit S1 of 0 and C1 of 1. C1 will be used in the next step, in the next operation, when we add A2, B2, and C1, which give us 1 plus 0 plus this 1. 1, 0, 1. And the result is again 1 for the carry, 0 for the sum, and so on. And what's the result of this addition then? These digits. So most significant digit is the last one. 1, 1, 0, 0, 1. 1, 1, 0, 0, 1. And if you want to write that as in the form of a computer program, again, this is the corresponding pseudocode for that. Now, all of these operations can be used for simple encryption algorithms, and I'll show you a simple example of that. Initially, so for this very simplified example, what we do is we will assume that the message consists of only capital letters. Think of each letter as a number between 1 and 26, and apply an invertible modular function to each number, so that we can convert back to letters. So like this. So basically, I've mapped the letters of the alphabet to the numbers from 1 to 26. So then what we do is we define and we decide on an encryption function. In this particular function, you get to choose. When I think about that, I think this should actually be from 0 to 25. Actually, yeah, 0 becomes 26. Yeah, it should be from 0 to 25. 0 to 1. This should be a 1 to 25, I think. Anyway, so we define an encryption function, and it has two parameters, 3 and 9. This kind of function as an encryption key for this scheme. We know, of course, the number of possible symbols or letters that we have, 26. That's where this mod 26 comes from. And this is the encryption function. So let's say we have a message, stop thief, that we want to, the plain text message, the unencrypted message, stop thief, and that we want to encrypt that. First step, we map each of these letters to its corresponding number. So S over here is 19, S becomes 19. So if you see over here, T follows that 20, O is 15, P is 16, T is 20, H is 8, I is 9, E is 5, and F is 6. That's how you get that. And then going from here to here is basically where we use this encryption function. So you multiply each digit, so 14 for example. 14 is basically A over here. Multiply by 3, add 9, and take the mod of 26. And that remainder becomes a number which is, so you use 19 as input. You use 19 as input. 3 times 19 plus 9, mod 26. The result turns out to be 14. That's what this is over here. 14 maps to the letter N. And so in the encrypted message, that letter is S is now replaced by N. And you repeat that for all the letters in the message, and you end up with this message over here. NQBEQGJXA, which has nothing to do with English. Okay, that is all about number theory that we're going to do in this course. And that's all of chapter 4 that we're going to cover here. And I'll see you in class. Thank you.